Today, we're going to delve into the concept of a vegetated filter strip, often abbreviated as VFS. This is a crucial component within green stormwater infrastructure, and you can find it detailed in Appendix O, Table 1 of the applicant's handbook. A VFS is typically designed and installed adjacent to impervious surfaces, such as highways and large parking lots. Its primary application is particularly effective in areas with high water tables, where the system is designed to manage groundwater percolation, ultimately returning that treated water to a surface discharge. Essentially, it acts as a natural buffer, filtering runoff before it re-enters the water system. Welcome to this module. Our main goal here is to help you understand where vegetated filter strips are used and, importantly, how to calculate their average annual effectiveness. We'll start by defining what a vegetated filter strip, or VFS, is and exploring how it functions in water quality management. These filter strips are actually one of 13 widely accepted best management practices here in Florida, often seen as a crucial buffer right next to traffic lanes, typically bordering a 12-foot wide shoulder. You'll then learn how to navigate the necessary tools, input data for an annual mass removal analysis, and interpret the output to assess the filter strip's performance. We'll walk through an example project together, and finally, you'll learn how to save your data in the appropriate BMPT file format for future reference. The vegetated filter strip, or VFS, is a specifically constructed and maintained area of vegetation. It's strategically located between sources of runoff pollution, such as roads, parking lots, or agricultural fields, and a receiving water body. The primary purpose of a VFS is to remove non-point source pollutants, especially nutrients. To effectively achieve this, a VFS must incorporate a media designed for nutrient removal. The treated discharge from a VFS ultimately flows into a surface water body. For most assessments of effectiveness, the VFS is considered a standalone system because its area, combined with the contributing area, makes up the total catchment area. It's important to differentiate a VFS from a vegetated buffer. While both involve vegetation, a VFS is a constructed area that has been impacted by human activities, whereas a vegetated buffer is typically a natural area with no construction or significant human alteration. These principles can be applied in various real-world scenarios, such as managing stormwater runoff around individual homes or housing units, alongside roadways, and within parking lots. When considering the implementation of vegetated filter strips, it's crucial to understand their locational limitations. The slope of the filter strip, measured in the direction of water flow, must be maintained between 2 and 20%. Furthermore, each filter requires a minimum width of 15 feet to ensure its effectiveness. The specific data and research guiding these applications, including details on hydraulic and nutrient removal performance, come from various federal, state, and local sources. This slide illustrates a specific design commonly employed to meet total nitrogen and total phosphorus targets. It typically incorporates a BAM mix in its construction. We have data supporting the effectiveness of these designs up to a maximum width of 30 feet. Most iterations of this design operate without an underdrain pipe, allowing the water to percolate naturally into an adjacent ditch, ultimately discharging as surface water. The efficiency and performance of such systems, particularly their runoff and absorption capacities, have been rigorously identified for Florida conditions and are documented in published research, as referenced here by the work of Mohammed Shokri. We're now looking at the details of a specific project, which is a 2-acre roadway located in the Tallahassee area. This project is expected to be part of a BMAP program, and our primary goal is to calculate the removal of total nitrogen and total phosphorus for a specific vegetated filter strip, or VFS design. We'll be using user-defined event mean concentrations, or EMCs, from an adjacent roadway. The design of this VFS includes a 1-foot deep biologically active media, or BAM, with a storage capacity of 0.38 inches per inch, and it's designed with a 4% slope. This VFS is capable of storing 6.6 inches of runoff, which translates to a curve number of 60. This curve number was derived using the formula of storage equals 1000 divided by the curve number, minus 10, the directly connected impervious area, or DCIA, for this project is 70%. The core question we need to answer is, what credit in terms of pounds removed per year can be assigned to this VFS? While the environmental resource permit for this project claims to meet performance standards of 55% TN removal and 80% TP removal, for a BMAP program, there's a specific need to calculate the average annual removal. Regarding the project dimensions, the total catchment area must equal the contributing area plus the VFS area. The length of the area is 1,013 feet. The width of the roadway DCIA is 60 feet, and the width of the VFS itself is 26 feet. When we check these dimensions, 1,013 feet multiplied by the combined width of 60 plus 26 feet, divided by 43,560 square feet per acre, confirms that the total area is indeed 2.0 acres. To perform these calculations and determine the average annual removal, we will be utilizing the BMPFast software, specifically focusing on its Vegetated filter strip module. The upcoming slides will detail the data inputs and the resulting outputs from this analysis. When entering the site and watershed data, remember that the site data specifically refers to the location of your project. An important point to keep in mind is that the use of a vegetative filter strip, or VFS model, assumes that water does not infiltrate into the ground. This means there's no requirement to conduct a groundwater analysis as part of this process. The best management practice, or BMP analysis, should always be performed on the post-condition land use scenarios. All of this input data, for both the site and watershed, must be carefully checked for accuracy within the context of this project. Here, you will input the specific physical dimensions and media treatment data for your system. It's crucial to pay close attention to the constraints on the data. For instance, the slope must fall within a range of 2 to 20%. If any input value exceeds these predefined limits, the recommendation is to use the closest limit value in the software. As an example, if your VFS width measures 35 feet, you should enter 30 feet into the software. However, remember there's also a minimum width for a VFS, which is 15 feet. You cannot use a width smaller than this. Once the data is entered, the removal efficiency will be displayed in kilograms per year. Once you have finished entering the configuration data, which includes selecting your routing and best management practices, you will then proceed to the summary section. The VFS for this particular highway has met the percentage removal required by the ERP. For the BMAP credit, the total nitrogen is 7.64 pounds per year, and the total phosphorus is 0.789 pounds per year. Remember to save your project data once you've completed these steps. So, what have we learned about vegetated filter strips? We've covered that a filter strip is a crucial tool designed to remove pollutants from runoff water. When implementing one, it's important to remember that the total catchment area must encompass both the contributing area and the vegetated filter strip itself. These systems often utilize a select media to effectively reduce the concentration of pollutants in the runoff before the treated discharge enters the surface drainage system. Beyond just understanding what a VFS is, we've also navigated the process of entering the necessary data for an annual mass removal analysis into our software and learned how to interpret the resulting output. Our example project highlighted the practical value of VFS, demonstrating how removal percentages align with the requirements for environmental resource permits, or ERPs, and the significant credit that can be assigned to these systems within Basin Management Action Programs, or BMAPs. Finally, remember the importance of saving your analysis data as a BMPT file. This will be invaluable for future use in permit applications and project documentation. This concludes our module on vegetated filter strips, or VFS, and how to evaluate their effectiveness using the BMPFast tool. We encourage you to explore other learning modules if you wish to deepen your understanding of related topics. When you feel ready, you can apply to take the competency test. For full details on the testing process, please refer to the module specifically titled Self-Test. Thank you for your participation.